Thank you. Today I'm going to be telling you about our work on Galois Transformers and Modular abstract interpreters, and this is joint work with Matthew Might and David Van Horn. So I want to start by, sorry, I don't have my presenter notes. How do I do that? Apologies. Should I wing it? How do I do this? I'll wing it. Sorry about that. Okay, so let's start. Program analysis. You're designing one, and there's lots of choices that you have to make when you're designing this program analysis. And the reason is because a lot of these choices that you make, there's no strictly better choices than others, and the reason for this is that you're constantly trading precision for performance. You know, do I make it context sensitive? Do I make it flow sensitive, path sensitive? There's no right answer. It depends on your application. And if you've implemented an analyzer, you know that these implementations are very brittle and difficult to change from a design standpoint. If you want to make a change in the design of your analysis, you may need to rewrite the entire system. That's a gross overstatement, but a large part of the system is common. So to address these challenges, we introduce building blocks called Galois Transformers. These are reusable components for building program analyzers. And as a bonus of using these tools, you'll get variations in the path and flow sensitivity of your analysis completely for free. So I want to walk you through what I consider one way of sort of designing an analysis from scratch, and this will be in the paradigm of abstract interpretation. So the first step in designing an analysis is you pick some programming language or a set of programs, and let's actually go through this program and see what it does, because I'll be showing analyses over it. So this is a safe function, and by safe I mean there are no division by zero errors. So we have a parameter n, we don't know what it is. We compare it with 0. In the case that it is non-zero, we assign x to be 0. If n is 0, then we assign x to 1. In the second if statement, we compare n with 0. If n is non-zero, then we divide 100 by n, and that's safe because we've ruled out n from being non-zero. And in the case that n is 0, we divide 100 by x. And this is also safe because there's a correlation between the values of n and x must be 1 in the event that n is 0. So there are no division by zero errors here. Now, the next step in designing a program analysis is you need a program analysis property in mind. If you go designing analysis without a property in mind, you will be lost, and you will be redesigning once you actually pick a property. So a possible next step is to pick a simple step is to pick an abstraction for the values that flow around in your programming languages. So here, a value that we were interested in was integers, and there's an infinite number of them, and our analysis needs a finite approximation. So I'm going to use this very simple sign analysis that says a number was either negative, 0, or positive, but our approach generalizes to arbitrarily complex domains. And I would read this as the integers are more precise than this abstraction of signs. That's how you should read that partial order. So the next step is where all the magic comes in. You implement it somehow, and maybe you pull the algorithm out of a textbook or a research paper, and this is where all those design choices come in. And I'm glossing over this, and I'm aware of that. And then you run the analysis that you implemented, and maybe you get some results out. So here's a possible set of results. N could be any number. X, we know that x can't be negative, but it could be 0. Y could be any number, and the analysis then says, oh, there's two potentially unsafe divisions in this program, division by n and division by x, because they could be 0. Maybe you after you're done running your analysis and tuning it, now it's time to prove it correct for some people, not everyone. And this usually looks like setting up a proof where the behavior of the program is contained in the over-approximation that your analyzer produced. So there's my template for designing an analysis. Let's look at these results and look at why they weren't the ones we wanted or the best ones. So the reason why we got this analysis is because it was a flow-insensitive analysis. And we know it's a flow-insensitive analysis because there's a global mapping from variables to the values that they may take on at any point in the program. Now, this isn't a bad analysis. It's actually a very fast analysis, but it's imprecise. And there's a trade-off here. But if we want more precision, if we want to verify more of these division properties, we can increase the precision by moving to a flow-sensitive analysis. Now, a flow-sensitive analysis is going to have the set of results that are present at every program point of our program. So a set of analysis results might look like this, where at program location 4, we know that x is either 0 or positive. Inside the true branch of program location 4, we've refined our knowledge on n, and we now know that it cannot be 0, therefore that division is safe. But we don't know anything precise about x from the correlation of n being equal to 0. So in the false branch at line 5, x really could be 0 from the perspective of the analysis, and we're unable to verify that one. So we can keep going even further. So we can get more precision and less performance and move to a path-sensitive analysis. And the way a path-sensitive analysis works is that you consider a set of results for every program location. So here there are two paths through the program considered at program location 4. One where n was non-zero and x is 0, and one where n is 0 and x is strictly positive, cannot be 0. And this analysis is able to verify both divisions of the program. So say you've gone through this loop of designing an analysis and you want to change these results. What do? Well, there's good news and bad news. You can reuse your choice of abstraction for values. And this is a classic technique in abstract interpretation of a tuning knob you have to vary the results of your analysis. But potentially, you may need to throw out your implementation and almost certainly your proof of correctness. Furthermore, say you wanted to change the programming language that you're analyzing. Now here there's I can say with more assurance there's good news and bad news. Still, you can reuse your abstraction for integers, but it's more likely that you'll need to throw out more of your implementation and proof of correctness, almost entirely. So to me, these are problems worth solving because these things happen, these changes in your design. How do you change the path and flow sensitivity of your analysis without redesigning from scratch? You may want to do this to prototype the precision and performance trade-off. How do you reuse machinery between analyzers of even different languages? And how do you translate proofs between each design? To solve these problems, we formed a marriage between two previously known concepts, one of Monadic Transformers, which are tools for building compositional interpreters. The other is of Galois Connections, and those are tools for building compositional abstractions for abstract interpreters. And you put these together, and you get a nice tool set for building compositional abstract interpreters. So I know what you're thinking right now. What are these things? What are these weird concepts I've never heard of before? And I'll explain them to you. So what's a monad? Let's start with that. And everyone tries to explain what a monad is, and I'll fail equally as everybody else. So I'll give it a shot. So a monad, I believe, is a module that contains a type and it contains some code. And it's an interface that looks like this. So inside this interface, there's a type operator, m, that's the monad, and a semicolon operator that some people will call bind. And then it has an effect operation interface, like get and put for some cell of state, and maybe failure for some kind of failure effect. But this is just an interface. And I would read the type m of t as a computation that performs some effects and then returns something of type t. So I'm going to show you monads by example. We're going to write a monadic interpreter for this programming language that this program was a part of. So we're going to write an interpreter for this language. We need a piece of state flying around, which we'll use in our effect interface. And that state is the environment, which mapped variables to values. This is the concrete interpretation of this program. And our value space will be integers and booleans. The monad that we use has the standard semicolon operator, which people call bind. And then the effects we need are get and put, those state effects for the environment, failure, and we'll use failure when the semantics of interpretation is undefined. This interpreter is going to be a small step interpreter, so it consumes an expression and outputs the next expression to evaluate. And it'll perform some effects along the way, which is what the M is for. So to interpret an assignment statement, we use this do notation for that semicolon operator. We interpret the atomic expression, which I use this Oxford bracket operator for, which performs effects because it needs to look up things in the environment. I get the environment, I update it to map the variable to the new value, and I return skip, signaling that there is no next expression to evaluate. For if statements, it proceeds similarly to assignment, where it evaluates the atomic expression. And these atomic expressions are like comparison with 0 in division. And we look at the value that came back, and we return the relevant branch if a Boolean came back. And if something else like an integer came back, we fail because the semantics are defined, or it gets stuck, right? So that's a concrete monadic interpreter by example. But we're interested in abstract interpreters, so let's abstractify this to get an abstract interpreter. The first step in that is to follow the abstraction we used for our values. So we're going to abstract the values that flow around in our environment to represent the sign of the actual concrete integer that took place during execution. And that change propagates through the environment, which now needs to be an abstract environment, and the monad, which now needs to be an abstract monad. The next step is to join the results in the environment when we update it. This is to have a sound over approximation of the concrete environments that were present in the concrete interpreter. The last step is the interpretation for if. You'd expect an abstract interpreter to potentially need to analyze or execute both branches of the if statement. The way you handle that is we introduce, or you, when you're writing this, would write a function called choosebool. This returns all of the concrete booleans that are represented by that abstract value. So the way to read this function is we evaluate the atomic expression, we extract all of the concrete values which could have been represented by v, and then we do our branch as before. Now choosebool will return multiple times if it's possible that multiple booleans actually flow to that value. And in order to implement choosebool, we need to introduce another type of effect, which is a non-deterministic branching operator. And so we need this box plus, which is for non-deterministic branching. So that's all there is to writing an abstract monadic interpreter. And this is a perfectly fine abstract interpreter. You can execute it, and you'll get an analysis. So to summarize, here's the recipe. You start with a concrete monadic interpreter. You abstract the value space, hopefully to something finite if you want a computable analysis. You join results when you update the environment to have a sound over approximation of your concrete environment. And then you need a non-determinism effect and non-determinism operators like choosebool in order to implement control flow. Now, you're probably wondering, why monads? Why are we using monads at all? Now, the first bullet is my opinion. I believe a monadic interpreter can be simpler than a state machine or a constraint system. That's up to interpretation. But the next 2 points are not. There were 2 effects that we used in this interpreter, state and non-determinism. And these allow you to encode arbitrary small-step state-machine relations, which are a nice kind of foundation for thinking about analyses. And there's a long tradition of doing that. And more importantly, if we don't commit to an actual implementation of that abstract monad, rather we leave it as an interface that you plug into the interpreter, then different choices of the monad will actually give you different useful analyses. So that's what a monad is. It's this module that contains a type and some code and maybe some effects. And it's an interface that we use when we write a monadic interpreter. Now, what are transformers? If we go back to those 2 effects that we needed, these are the only 2 effects we need for writing small-step monadic interpreters. For each of these effects, there's an effect interface that they come with, and we saw these, get input for the state, and failure and this branching operator for non-determinism. For each of these effects, there's a monad transformer that implements that effect. And the way you use a monad transformer is you start with some existing monad that maybe has some effects inside of it, and you put a transformer on top, and what you get is a new monad with an extended effect interface. So this monad on the right-hand side has the effects from before, plus we've added state to it. Likewise, you put a non-determinism transformer on top of that monad, and you've added non-determinism effect to that monad. So we had this actual monad that we needed for our interpreter. Let's build it. You can start with the identity monad, which is very simple, and it has no effects, but it supports the semicolon bind operator. We can add non-determinism on top of that to get failure and branching in our effect interface. And we can add state on top of that to implement this full effect interface. Now, the monadic abstract interpreter we needed required an abstract monad. And this is also very easy to do. We just carry around a piece of abstract environment. And this is all we need to plug into our monadic abstract interpreter. And this monad right here, if we plug it in, this will give you a path-sensitive analysis and state space for the abstract interpreter. Now, the order that we use to build this monad does not matter in terms of the effect interface. It matters for the analysis, but we can rearrange these, and what just falls out of the monad transformers is a flow-insensitive analysis. So this is a large part of what this paper is about, is getting these different analyses from the orderings of the monads in the stack. So here are 2 that came from purely the ordering, and you can prove that there is a partial order here where flow-insensitive has less information than a path-sensitive analysis. To get a flow-sensitive analyses, we implemented a new transformer called float. And it's a combination of non-determinism and state in one monad transformer. And the cell of state that it carries is going to be treated flow-sensitively. Now, the way that these transformers actually end up giving you these analyses are the types that they synthesize for the monad itself. So for the flow-insensitive analysis, the type that gets synthesized has a single global environment. This is purely from the types. The flow-sensitive one, float, it builds maps from expressions to environments. This is the mapping from program location to analysis results. And the path-sensitive ordering gives you a map from program locations to sets of results, one for each path through the execution. And I want to take a moment and say that you might be wondering what other orders are possible. And in a sense, these are the only possible orders in this picture. So key points are that you only need one non-determinism effect in the entire stack. And all of these have one place where non-determinism happens. And then the three choices are where state shows up. If state shows up underneath non-determinism, then that state will be flow insensitive. If state shows up inside of flow T, then that state will be flow sensitive. And if state shows up above a non-determinism effect, it will be path sensitive. And you can actually interleave these so that your analysis is flow sensitive for parts of its state space and path sensitive for others. So you have more fine-grained control. So if you plug these into our interpreter, you get this nice spectrum of analyses of varying precision and inversely varying performance that you may be interested in. So to summarize, to build a monad, you construct it using these three monad transformers. The order matters in that they yield different analyses, but every order will give you the same effect interface that you can plug into your interpreter. And this allows you to rapidly prototype this precision and performance trade-off of path and flow sensitivity. Now, why transformers? Well, we reached for them because they're a well-known technique in the literature for compositional semantics and interpreters. So we just brought them over directly and applied them to abstract interpreters, and they fit the bill just great. And the reason why I think they're useful is they allow you to reuse the analysis machinery. Different abstract interpreters use these same three monad transformers. So you get reuse across different analyzers. And then even for a single analyzer, you get variations in the analysis by changing the order and the types of monads in the stack. So those are Galois transformers. They're these pluggable components that you use to build monads. And this is, I think, extra important to people who've built their own monads. It's hard work designing your own custom monad, and you don't have to. You get to use these pre-existing monad transformers from a library. And they snap together and build monads that you need for your monadic interpreter. So what are Galois connections? Well, if anyone was at lunch with me yesterday, you'll know I can't spend less than 30 minutes talking about this. So I won't tell you what a Galois connection is, but I'll tell you how we use them and why they're important for us. Galois connections are a compositional framework for proving correctness of abstract interpreters. And we build two sets of Galois connections alongside our transformers. And they serve two very important roles. The first is actually an executable code. We execute these Galois connections in order to execute our monadic analyzers. This is related to finding the least fixed point of a transition system. We also use these Galois connections for building proofs alongside the transformers to get a large part of the correctness proof of your analyzer built automatically for free. And you'll need to see the paper. There's a rather substantial proof framework. So Galois transformers are these monad transformers, plus the Galois connection properties that we build alongside them. And the Galois connections, again, are necessary for execution and for proofs. And I'll point out right now that flow T and non-det T are both purely fine monad transformers even outside the context of analysis, so they should be useful for even non-abstract interpreters. Non-det T, there's kind of a running attempt in defining the right list monad transformer or non-determinism monad transformer. This is different than anything I've seen in the literature so far, and I think this might be it. There's more details in the paper, and if you have more questions, you can ask me after. So putting it all together, here's my design recipe for you. You design a monadic abstract interpreter. You instantiate it with monad transformers. You get to change those monads to change the actual mechanism of the analysis, the path and flow sensitivity. And then we build these Galois connections for you for free that give you an execution engine and a large part of your proof framework. So we've implemented this. It's a prototype. You can play with it right now. The Galois transformers really are a semantics independent library that you bring over to your semantics that you're analyzing. And I want to note that Haskell's support for monadic programming was helpful, but it's not necessary. You could definitely implement these in any other programming language. I guess you would need higher order functions. That's pretty much all you need. So here's what I hope the picture will look like, at least for path and flow sensitivity, right? I'm cheating. This is not all changes you want to get to your analysis. But if you want these three variations that really have drastic trade-offs in precision and performance, you get to keep your implementation and you get to keep your proof of correctness. And I think that's pretty cool. Furthermore, if you change your programming language, you still need to write a new monadic interpreter, but the monad transformers and the proofs that they construct also carry over. So you get parts of that translates over for free. So that's all I have. There's some future work that we want to keep working on this. I'm only going to spend time talking about this last point. We're interested in actually verifying this framework in a proof assistant like Coq or Agda. And we think this is exciting because verifying abstract interpreters is particularly challenging and suffers even more from this change in design, redesign problem. So we want to get working on that, and the first step there is mechanizing Galois connections, which is already kind of a hard problem. So if you're interested in our first steps at tackling that problem, we have a draft that you can see. And that concludes my talk. Thank you.
Okay, let's thank David. Questions?